Hi, my name is Betsy Jameson, and I'm going to do a quick little video here about the quantum number rules. So we'll be talking in class more about where the quantum numbers come from and a little bit more about what they mean. Some of the quantum numbers come from solving the Schrodinger's equation. But, for the purposes of this video, I think all you have to know is this point here, that the quantum numbers are, they have rules and they're going to give you information about your atomic orbitals, in particular, things like the size of the orbital, the shape, things like that. So again, you'll get more context about what the quantum numbers are telling you in class, but for the purposes of this video, we're just going to go ahead and talk about what the rules are. So there are 4 quantum numbers, and we're going to go through them one at a time. The first quantum number that I want to talk about is the principal quantum number. So the principal quantum number is n. So I'm going to write that down here. So it's a lowercase n. And the rules for n are pretty straightforward. N has integral values. So n can equal, it starts with number 1. So 1, 2, 3, 4, 5, and so on and so forth. So essentially, the rules for the principal quantum number n, you start with 1, and then you just go up in integers. So n can be 1, 2, 3, 4, 5, 6, 7, 8. It goes from there. So that's the rules for that. I will tell you, again, we'll talk more in class, but the n, the principal quantum number value, is related to the distance from the nucleus and the size of the orbital. And I will just mention that the larger your n value, the farther, so if an electron is in an orbital with a larger n value, it's going to be farther away from the nucleus, and that atomic orbital will be bigger. But again, we're just going to focus on the rules here. So principal quantum number n, you start with 1 and just integer values up from there. So 1, 2, 3, 4, 5. So our second quantum number is the angular momentum quantum number. It tells you about the shape of the orbital. And for the angular momentum quantum number, we call that L, and we usually write it as a little cursive kind of L like that. L can have values from 0. So the values here, they go from 0 to, and they're going to be integer values, to whatever your n value is minus 1. So in order to know your L value, you have to know what your principal quantum number n is. So for example, if n equals 1, you know that your values are going to range. They're going to start at 0 and go to n minus 1. So you say, okay, what is 1 minus 1 at 0? Oh, okay, so the only L value you can have is 0. If n equals 2, L can equal 0, and then it goes up to 2 minus 1, which is 1, right? So in this case, you can only have values of 0 and 1. If n equals 3, your L values, they're going to start at 0, it's going to be 1, and it's going to go up to 2, right? Because 2 is 3 minus 1. So this is how it works. So essentially, to do your angular momentum quantum number, which is going to tell you about the shape of the orbital, you have to know what the n value is. You start at 0, and the possible values start at 0, and they go to n minus 1. And again, they're integer values. Now, it turns out that with this angular momentum quantum number, we actually give names to some of these L values, and I'm going to tell you about that on the next slide. Okay, so, this is sort of our L slide continue. So when we think about our L value, like I said, these are going to give names to the different orbitals and their shapes. So the L values, they start at 0, and then the next integer value would be 1, 2, 3, 4. I'll go up that high. And then the name that's going to go with them, right, these are going to end up being the names of our atomic orbitals. So for the 0 value, the name we give to that is S. For an L equals 1, we call that P. For L equals 2, we call that D. For L equals 3, we call that F. And then we start going alphabetically after that, G. If L were equal to 5, this would be H, and I'll just put little dots here. It turns out, for some interesting reasons, we would skip J. But the ones that we're going to really be focused on in Chem 111, and the ones that kind of make a big difference in chemistry are usually these four here. Maybe you've heard of atomic orbitals, that like an s orbital, a p orbital, a d orbital, or f. These are the ones that we have. Those are going to be the ones that you're going to come across the most. And I'll just tell you, it's kind of weird, like where do these names, why would you start with S and not A in the alphabet? Well, it turns out that they're historical names and they come from the lines of atomic emission spectrum. So the S stands for a sharp line, P is a principal line, D is a diffuse line, F is a fundamental lines. And so it kind of is like a historical name. Again, it came out of people looking at atomic emission spectrum like we saw with the hydrogen lamp. So L values get a name that goes with them. So an L value of 0, and I should get my little pointer out, an L value of 0 goes with an S. An L value of 1 goes with a P. An L value of 2 goes with a D. An L value of 3 goes with an F. And again, we'll talk more about that in class, but these are the rules. Our third quantum number is the magnetic quantum number. And this one is going to tell you, the book likes to talk about this being the orientation of the orbital in space. I like to think about it as how many of each type of orbital you have, right? So sometimes you only have one of each type of orbital, sometimes you can have 3, sometimes you can have 5, and this magnetic quantum number is the one that tells you that. And again, it kind of tells you orientation. You can think about that as being sort of like the direction it's pointing in space. And again, this will come clear as we talk more about atomic orbitals. So again, this video is focusing mostly on the rules for how you do the quantum numbers. Again, you'll get more context for this in class. Okay, so our magnetic quantum number, it's an M, and then we do a subscript L, and we usually write it as a little script there. So this is M sub L. And the values here, you have to know what your L value is. So the M sub L, the values here, they range from negative L to positive L, and they're going to be integer values. So if L equals 1, M sub L values, they start at negative L, so that would start at negative 1, and then they would go, you just basically keep going up in integers. So the next number after that integer value would be 0, and then it goes to positive L, which would be plus 1. So you have to know your L values. M sub L values range from negative L to plus L. If L is equal to 2, your M sub L values, we start at a negative L, so we'd start at negative 2, and then we'd go to negative 1, 0, positive 1, and positive 2. So in order to determine your M sub L value, you have to know what L is, just like the L value depended on N. So again, just integer values from negative L to positive L are the rules for M sub L. And I will make a little note here, right? I told you it's sort of how many of each type. Well, there are 3 values here, so that means you'll end up having 3 of that type of orbital, and there's 5 here, so you'll have 5 of that. Again, we'll do more of this in class, but this is just the rules of how these quantum numbers work. And finally, our fourth quantum number is the electronic spin quantum number. And this is actually one that has to do with the charge on your electron. So we know that electrons are negatively charged and they actually spin on an axis. So this one is M, but it's a lowercase s value. And this one is all about, you have a spinning electron, right? And when you have a spinning electrical charge like that, it acts like a magnet, generates a magnetic field. So maybe you've heard about sort of like right-hand rules in physics if you've ever taken that. Basically, you have your spinning electron. It can spin clockwise or counterclockwise. And because of that, it will get there's only 2 values because you can either spin clockwise or you can spin counterclockwise. Gets you 2 values, and so the M sub s values are either plus 1/2 or minus 1/2. Those are the 2 values that it can be because your electron can spin basically in those 2 different directions. So electronic spin quantum number has to do with the fact that we've got a spinning electron. The electron's got that negative charge, and again, it can spin clockwise, it can spin counterclockwise. 2 values, plus 1/2, minus 1/2 are the rules for that one. And on the next slides, we'll do a couple of examples where you can apply these rules. Okay, so now we'll do some examples. And again, here's the question up here. When you have an n value, we're just applying the quantum number rules. If your n value, your principal quantum number is 3, I'd like to know what different values of L can an electron have when the n value is 3. So if you want to give it a try on your own, go ahead and stop the video now, and then come back and you can see my solutions. Okay, so thinking about the n value, right? We know our n value is equal to 3. We know that the rules, if n is equal to 3, we know L goes from 0 to n minus 1, which in this case, right, we know in this case it's going to be 0 to 3 minus 1 is 2. So if n is equal to 3, our L values can be 0, 1, or 2. And so it can have those 3 different values. L is equal to 0, 1, or 2 if n is equal to 3. Okay, our second example here, again, if your L value is equal to 1, I want you to apply the rules and see what different m sub L values you can have for an electron. So again, if you want to stop the video, go ahead and stop the video and figure out when L is equal to 1, what m sub L values can the electron have. Okay, so if L is equal to 1, we know m sub L, it has values. It goes from negative L to positive L. So if L is equal to 1, m sub L is equal to negative 1, then we go to 0, and then we go to positive 1. And so this would be the answer. If L equals 1, m sub L equals minus 1, 0, and positive 1. Okay, so this last example is a little more complicated. I want to know the quantum numbers for each of the 2 electrons in a 4s orbital. So you can see that this is not just as simple as the last 2 where you're just applying the rules. So we're going to have to do something with this 4s orbital. So if you want to give it a try on your own, go ahead and stop the video now, and then you can resume it and listen to my explanation. Okay, so the key here is that I have a 4s orbital. Now, this 4s, the 4 is going to tell us the n value, so n equals 4. And the s, you might remember, is the name. The s is going to tell me about the L value, right? So you might remember I had that chart where I said L is equal to 0, 1, 2, right? And you might remember I said the name is SPD, and we kind of went on from there. So that's the part that's going to be there, right? When I'm talking about a 4s orbital, I know n is going to equal 4. Because it's an s orbital, and I'm going to go ahead and just kind of do that. Because it's an s orbital, I know that the L value is going to equal 0. Okay, so that's what I get out of this name 4s. Now I have to go a little bit further and I say, okay, I want my quantum numbers. I know there are 4 quantum numbers. Okay, what's the m sub L value going to be? Well, if L is 0, m sub L goes, right, it ranges from minus L to plus L, but in this case, L is 0. So m sub L is also going to have to be 0. And then I've got 2 electrons. One's going to be spinning clockwise, one's going to be spinning clockwise. I know m sub s can equal plus 1/2, right, or minus 1/2. So in this case, the 2 electrons, 1 electron, so 1 electron will have the quantum numbers, and I'm going to kind of put them in order. The n value first, so it'll be 4, 0 for the L, 0, and then the plus 1/2, right? So that's the n, L, m sub L, and the m sub s value. And the other electron will have the quantum numbers 4, 0, 0, and then this one will be slightly different. It'll be minus 1/2. So again, this example is a little bit harder because you had to start with the 4s orbital, and so from the 4s part, from that name of the atomic orbital, you find the n value and the L value. From there, you find the m sub L, and then 1 electron is going to be plus 1/2, 1 electron is going to be minus 1/2. So the final answer here is this part. And again, it's applying the rules, but it's also kind of taking it and starting with this name up here of the 4s orbital. So the 4, right, goes with the n. That S tells you about the L value. From the L value, you go to M sub L, and then you know M sub S is either plus 1/2 or minus 1/2. So one electron will be a plus 1/2. The other one will be minus 1/2. So these two electrons, 3 of their 4 quantum numbers are the same because they're in the same orbital, but one has an M sub S of plus 1/2, one is minus 1/2.